I have talked about Kjeldahl so much that my jaws are hurting. I know, and your wrist is probably hurting due to the notes that you are taking because you are trying your best to pass that quiz and you're going to try your best to get an A. And you know that when I give you that A, you're going to sit back and you're going to laugh because you know how much I hate giving out an A. And you're going to be like, ha 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 ha, the joke's on you this time, buddy. Okay, so in this video I told you I'm giving you details of the Kjeldahl and what goes on in the Kjeldahl situation. So the first thing I'm going to do is talk about the breakdown of the individual steps, and then I'm going to give you details on the reagents, and then we'll go through and talk about the actual reaction pieces on how all of this shakes out. So the first thing that I want you to maybe pay attention to is the setup of the Kjeldahl. Ours might be slightly modified from the picture that you see, but all the basics are there. So what you're finding, like I've circled in the previous picture, is the K flask that's going to have your sample here. And that sample is going to be heated up. Now, it shows a Bunsen burner. You know as good as well as I do, we're not going to be using Bunsen burners. We hate Bunsen burners. We only use Bunsen burners when we absolutely have to. And those Bunsen burners can be a fire hazard. So we stay away from them, especially if we've got organics out with another lab and maybe somebody is bowling off some methylene chloride in the corner beside of you and you're going to whip out a Bunsen burner and create a fireball that happens throughout the entire... I sounded almost like Pitbull, didn't I? Fireball! So you're going to create a fireball through the lab space. And when you do that, well, that's bad news bears. So we use heating mantles and we use Variacs instead of Bunsen burners. So either way, that flask is going to get heated. That flask has your sample plus other stuff. And eventually we are going to add more reagents to it on the back end, and that will release ammonia. And that ammonia goes up, and then it will eventually go over, and then it will eventually condense, and we go into a receiving flask on the other side. So, pieces and parts, you know what the majority of these are maybe. The West condenser is going to condense, and then the drip adapter will allow you to collect, and then we have a elbow or something at the top that connects all of it together, and then we have this K flask that eventually is going to be heated even longer with more reagents after a certain point in time. All right, so with that said, let's talk about the very first step. And the very first step is using just the K flask. That is it, nothing more. So I don't really need the West condenser yet. I don't need that receiving flask. We have not made it to that point. The only thing that I need for the first part is the Kjeldahl flask with some sample and reagent in it. So in step number one, what we're going to add to our sample most of the time, and keep in mind there are modifications, most of the time what we'll add is sulfuric acid. And this very often is concentrated sulfuric acid, or if it is diluted, it's going to be diluted a little bit. It's not going to be a very weak solution of it, hence strong, concentrated. But sulfuric acid is going to get added, and sulfuric acid will decompose the sample. It will break down proteins, it will break down carbohydrates, it will break down fats, it will break down anything that it can with the help of heat. It will break down anything that it can and just really get it down to the basics. So imagine taking a cake and being able to deconstruct the cake back into the ingredients that made the cake up. That is what sulfuric acid is doing here. But sulfuric acid needs a little bit of help. It can't just do this on its own. It can't just decompose and go back to closer to an elemental ammonia gas that's going to get released. So what happens is that we also add a catalyst, and that catalyst very often is going to be copper 2 sulfate. Copper 2 sulfate is a catalyst, and the definition of a catalyst is a reaction will always need energy in order to go up and over the mountaintop, right? So what happens is that things will sit there and things might not react immediately. But if I give it a little boost, if I give it a little oomph, if I push that stone up the hill and I get it to the top of the hill and then let it go, then the reaction takes off. And I don't really need to be there after that point. But Jack and Jill goes up the hill, and with this sample they go. I mean, that's what's getting ready to happen here. So what happens with a catalyst is that it lowers what we call the energy of activation. Activation means it goes forward. So instead of this really high hump that I got to push things up, what happens is that a catalyst lowers that down, and maybe quite a bit, and it's just little up and over. I mean, that's it, right? I can just blow on it, and then it goes up the hill, and then down the other side it goes, and it doesn't come back. So the copper 2 sulfate is a catalyst because it lowers the activation energy that this reaction needs in order to decompose the samples. Whatever the samples are, it doesn't matter. Soil, water, protein drink, fertilizer in our case, doesn't matter. Sulfuric acid is going to decompose it, and that decomposition needs help, and that's coming from copper 2 sulfate, which lowers that activation energy down, so this can be driven forward. And this helps liberate the nitrogen that is in those samples, and that nitrogen is actually going to come out in the form of ammonium sulfate. So we've not really fully released ammonia gas, but we release the nitrogen, release the Kraken! We release the nitrogen out, and that nitrogen is going to react with the sulfate, with the sulfuric acid, of course, H2SO4, and we're going to get ammonium sulfate that begins to get formed. Now, ammonium sulfate, depending on how much is there, we could actually see it crystallize here. So there is a chance that through this heating process, with your part 1 of sulfuric acid and copper 2 sulfate, throughout that heating process, you might see crystals. And those crystals can sometimes be really chunky. They can sometimes be very flat. They can sometimes be very square. They can sometimes be very fine. They can sometimes float on top. They can sometimes float or sink to the bottom. I mean, it doesn't matter. If you're seeing something there that is solid looking, then there is a chance that those are ammonium sulfate crystals. So don't get weirded out. They are going to be there. It can happen, and it is kind of common. Some people don't see them at all, but other people will see them no matter what, and they're big and they're large sometimes. It's not an issue. So don't freak out if it happens to you. But that is the first step of the process of the Kjeldahl. Now, the problem is that this requires so much heat. Because look, they gave me a Bunsen burner, right? And I told you, we're not using a Bunsen burner. But heat is going to be required. So that heat, I don't want to be there forever. I don't want to blow the lab up. I don't want to blow fuses out. I don't want to mess with our electrical box. I'm not going to crank in the heat of a volcano in order to get this to go forward. So what happens is that one of these steps will very often add potassium sulfate. So the sulfate piece is good because sulfate is already there from the sulfuric acid. So that way we don't have complications. We're keeping our alphabet soup still with vowels, Pat. Buy me a vowel. That's what we're doing. We don't want the entire alphabet of chemicals in our containers when we do these tests. If we can find common ground between some of these ions, it's always going to be the better choice. So sulfuric acid is H2SO4 and potassium sulfate is a SO4. SO4 is already there for sulfuric acid. SO4 is going to come in with the potassium sulfate. Whatever. It doesn't matter. Who cares, right? That's a good thing, not a bad one. So potassium sulfate is a salt, and potassium sulfate does not have nitrogen, okay? So we don't have to interfere. We don't have to worry about extra nitrogen coming in from that salt. It's potassium, not an issue at all. Who cares? But that salt is going to be added because that salt will like to increase the boiling point of all of these things. So what's going to happen here is that we're going to heat. And that heat is going to allow us to heat it at a really hot temperature. And that salt is going to disturb all of our solvent, and that salt will break apart any kind of hydrogen bonds that might be present in that water sample, and that salt will allow me to heat and boil a little quicker. Now, that increase in boiling point is actually not in reference to the solvent, but that increase in boiling point is going to be in reference to some of the products that's getting generated from this reaction. So it's actually a twofold case or a twofold solution here. Get it? Solution. So salting a solution will allow us to heat much faster and get to a hotter temperature. But at the same time, some of these products that are forming, well, we're not going to release them. We're not going to escape. They're not going to leave very early on in the process. They're going to be somewhat trapped on the inside. And again, that's a good thing. That's what we want. So the decomposition is going to be completed when I take a look at my sample and the solution is actually going to be clear. Now, clear does not mean colorless. The solution could still be colored. So copper 2 sulfate is going to be a blue solution. Copper 2 sulfate, when it goes into these solutions, can actually come back out blue in the very end. And that's because the definition of a catalyst means it does not get used up. A catalyst is something that you put into the system and you get out of the system the same way, right? Into the system and you put it in and you can get it out because it's not actually been used, you know? So that's the definition, the proper definition of a catalyst. It lowers the hill, it lowers the hump, but that's all that it does. It does not get used up in the process. So in the very end, if your solution is coming back blue, not a big issue. I guarantee you a reaction still happen, but your copper is back to copper, and that's what actually should happen. But some people don't see the original start blue color. Some people might see like a blue-green color instead. That's not an issue either. Not a big deal, but it's going to be clear. You should be able to see through it and out the other end, even though a color still might be present. All right. So that's going to be step 1 and kind of step 2. So step 1 is add the reagents all in there. And then we're going to add our heat and our flame. We're going to heat it up. Step 2 is kind of the extended heat. And we are converting everything over into a product at this point. And now we go to step 3, which is getting ready to distill. And this is where the entire Kjeldahl setup now comes into play. We have freed up nitrogen in the form of ammonium sulfate. And that ammonium sulfate now needs to be converted into something that can be distilled off and captured. So what happens and what's required here is that sodium hydroxide is going to be used in this next step. And this is a very concentrated sodium hydroxide solution. From my mind, not looking at the procedure in front of me, I think that these are at least, if not greater, but at least 50%. So 50% sodium hydroxide, 25 grams of sodium hydroxide pellets, and 25 grams of water. I mean, it is half and half. So super concentrated solutions of sodium hydroxide. This alone is going to generate heat, and that heat is abbreviated with a triangle. And that heat from that solution alone is going to be so hot that maybe you won't even be able to handle it anymore. You will have to let it dissolve. You will have to let it cool down, and then you'll be able to do some stuff. But sodium hydroxide is going to be awful to prep on your own, and then that is going to have to be used in a container that has been heated for an extended period of time, that's got really high acid in it already, and that's got some water in there already, and these two are going to come together and they're going to make an even more violent reaction that begins to happen, and you'll generate even more heat when this thing begins to go forward. So just be careful, and you are going to add the sodium hydroxide slowly. slowly, okay? Now, when I do that, what I mean is that you're going to not dump it all in at one time. If you dump it all in at one time, this thing is going to explode, and this is where it does, and it's going to go all over your face and all over everything else that's around you. It's just like a volcano. I mean, that real long Kjeldahl flask is great for that. Out it goes. So you want to prevent that from happening, and you're going to add the sodium hydroxide in a very slow stream, not all at one time. So if you add it in a very slow stream, you prevent that buildup from happening and that violent reaction from taking over, and it's still going to get hot. It's still going to generate some heat. It will still be, oh my God, I'm going to blow something up. But you won't, I promise, I hope, maybe, who knows. When you do it, just don't let me be around in the same room, so that way I can make a really good escape out the front door when it begins to go forward. All right. But here's the catch. When you add sodium hydroxide, you have to be able to finish the lab up. I mean, there's no, okay, let's pause here from this point on. This is the turning point. So you can stop. It's not ideal, but you can stop up until this point, and you can put a cap on your solution. And then you can come in the next day and add sodium hydroxide. But once you add the sodium hydroxide, you have to finish. There is no going back after you do this. I'm sorry, it's the Matrix. There's no going back. Once you take the pill, you got to keep going. It's just the way it is. And the reason is that this sodium hydroxide is going to convert that salt into ammonia, and that ammonia is NH3, and that ammonia is a gas. So your job at this moment is to generate the gas, and now you are, and it's to make sure that that gas can turn somewhat back down into a liquid. And if not, at least you got your drip adapter submerged into a solution that can capture that ammonia on the other end. So, with that said, everything is temperamental from this point on, because you're working with a gas, not a liquid, and not a solid. Not even a volatile liquid, a gas. So, you got to work quick in a way, and you got to make sure that you're there with it as much as possible. So, that is what's leaving the flask. That's what's traveling across into the condenser, and that is what you're collecting on the other side. Now, over here on this collection flask, notice there's a solution in it, and that solution is very important. I'll talk about this in just a minute, but that solution is going to be something that can capture ammonia quite easily. So the ammonia is getting distilled, and the ammonia is getting captured, and that ammonia is now trapped. So what happens here is that the ammonia is a base. Right? Okay, so let's start talking about reactions now. So what's happening is that this ammonia is a base, and that base is going to be in a gas form. And inside of this flask, I've got a solution. And that solution is to trap ammonia. Well, what does that even mean? How's ammonia going to get trapped? Well, we don't actually trap it. We react with it. So in that receiving flask, there is very often an acidic solution. Again, different forms exist. Different modifications of Kjeldahl are out there. But it's going to be acidic most of the time. So this base, NH3, is going to go up and over. And drip, 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 drip. And those fumes go inside of that container, and that ammonia immediately reacts with an acid, and that gets it out of the gas form, and that gets it out of the problem stage where we don't want to deal with it because that's the gas form, and now it's a more workable solution that I can do things with. All right, well, what happens is that we have excess on this side. Quite a bit of it. We've got excess. And that excess acid is there for a reason. And that's because the ammonia is going to come in and kill. Ha ha ha, Chucky. It's going to kill the protein out. Or not the protein, the hydrogen out, the proton. And we are starting to deplete the levels of acid that is remaining in that flask. Now, we hope we don't get to a point where all the acid's just completely neutralized. But there's going to be a point, and again, modifications. There's modifications everywhere, and your lab directions might be worded a little different because it uses different reagents, and that's okay. But the basics that's happening here is that the ammonia is getting neutralized, and if this is very basic Kjeldahl with no bells and whistles, just straight up Kjeldahl the way that it is, that's fine. That base is going to eventually kill the acid, but there's going to be extra acid left over. And that extra acid can be quantified. We can actually calculate how much acid is left over. And the way we do that is that we titrate. And if we titrate, we can titrate with a base because we've got extra acid. And if we can find how much was actually used, or sorry, how much is left over, then we can calculate how much was actually used in the ammonia neutralization step. This is a back titration. It's how all back titrations work. And I've always said, throw a pizza party, you order 20 pizzas, someone gathered all the remaining pizzas up, and they gave you 6 back. And you're like, oh, I got 6 left over? Well, that means there were 14 that were eaten. Gone. That was probably due to one high school kid, right? 14 of them. I mean, I'll believe it. Okay, well, that's extra. You are calculating the extra that's left over, and you're doing a subtraction to figure out how much was used up. That's a back titration at its heart, and that's exactly what we're doing here and why we do many back titrations. Same kind of scenario here. It just so happens that the ammonia is a gas, and it's a problem unless we neutralize it and kill it out immediately to have something that's a little bit more stable or better to work with at this point. All right. All right. Again, modifications of Kjeldahl are out there. It's not the same every single time. And even your own lab directions might be worded or modified a little differently if we find out that at some point in some year that things work a little bit better, then we're going to give you that modification. But we're only focused on the basics for lecture and how this thing works. Titration requires an indicator, and I'll talk about the indicator here in just a second. But it is not phenolphthalein for the most part. I also showed you a little bit of instrumentation in the last video. So before I go a little bit further into the reactions and the heavy chemistry part of what we're doing, I also want you to know that these setups can kind of be semi-automated. So what you're seeing on the left-hand side is Kjeldahl without equipment and fancy bells and whistles. The Kjeldahl flask you still see back here on the end or on the back, racking just to stabilize the flask. Up here at the top is a connection that will eventually go up and over. So that way when you go to your distillation side, you're ready for that. And then the West condensers are here in front. And then that drips down into an Erlenmeyer flask that will have your acidic solutions mainly, most of the time, here at the bottom. All right, so that looks pretty good. A little bit cheaper, but still out of our price range. These things are still going to be $20,000, $25,000 just for a fancy little heat block that is made to hold more than one Kjeldahl flask at a time. Not a big issue. We can do this individually, but it's a little bit better than instrumentation. Okay. Over here on the right-hand side, you see kind of a similar thing, just made in a different way. Up here at the top are the Kjeldahl flask, and that Kjeldahl flask is going to get heated for a long period of time. Sooner or later, we'll open up the vent, and that will generate the ammonia, and that will go up and over. And on the back side of this are the West condensers that will eventually drip down into the receiving flask on the back side. So the concepts are there. It's just more conveniently placed, and it's a little more organized, and it looks a little more impressive in a lab if you do have one. But again, instrumentation is also out there for those people that process Kjeldahl all the time. Here's another picture of Kjeldahl, just more instrumentation based. So over here to the left-hand side, you'll see a rack, and there's a lot of glass tubes inside of this rack. This is an auto sampler. And then down below, you'll see the Kjeldahl flask with those solutions. Those will be heated, those will be digested, those will get prepped, they will get ready for the release the Kraken ammonia step, and then it will eventually go to a titration. Over here on the right-hand side, she's kind of covering it up a little bit, but that's going to be your titration area. So that will automate the titration for you as well, just like a regular automated titrator. There's no difference here. Does the same thing. And again, it's nice and it's convenient and it does it automatically. If you want better pictures of maybe single runs, because that was a multiple run, if you just kind of want to do one at a time, not a big deal. These are the kind of systems that you begin to look at. So you will often see a Kjeldahl flask get presented or a sample get presented. You'll see automated titration that will begin to happen, a collection of the ammonia gas. I mean, all the basics are just hidden really underneath a cover of an instrument, but everything is pretty much there. So they can go as fancy as you want or as basic as you want. It really depends on the user and what their needs are as a laboratory. All right. But either one of these, again, we do not have. And the reason is because we have issues. And those issues are money. And those issues are whoever wants to make a donation. So that way we can purchase these and make your lives a little bit easier. All right, so now what I have on the screen, one of the last slides that I want to show you, not the last, but next to last at least, are the 4 different somewhat reactions that go on in a regular setup for a Kjeldahl. Again, the reagents can be different, and that will change these chemical equations, of course. But for the basics of the basic, this is how the Kjeldahl works. All right, so first off, I'm going to have a sample, and this sample is actually a sample that can come from a food or a beverage or a fertilizer or soil or pig poop. I mean, it doesn't matter. It can be anything that it wants. If it's got nitrogen in it that can be released and can be measured, then go for it. Kjeldahl will do it. So that sample will react with H2SO4, and that, of course, is sulfuric acid. And decomposition begins to take place. And that decomposition will generate ammonium sulfate. So ammonium is a +1 and sulfate, SO4, is a -2. So that's why it takes 2 of the ammoniums to balance out the -2 of the sulfates, so that way they can make a perfect match made in heaven and be happy for the rest of their life. So this is the area where you might see crystals. And those crystals can form during the first area of the heating. Now, the CO2 is a byproduct. Doesn't matter. I don't care about that, right? You shouldn't care about that either. But CO2 is a product of this, and that product can be seen in the Kjeldahl flask as you begin to heat it. So don't be surprised if you see smokiness that takes place, some gas fumes that begin to form, because CO2 can be one of those products. SO2, sulfur dioxide gas, can be one of those products, and water vapor can be one of those products. So those are actually signs that the reaction's going forward. Those are a good thing. So we're going to heat this digestion flask up, the Kjeldahl flask, and we will see things happen to my sample. But we will also see things that are getting released, and those are going to be white fumes, and they're going to be swirly, and it might be a lot of them. But that is perfectly okay. That is not your ammonia. So don't freak out. It's not your ammonia at that point, because your ammonia is actually ammonium sulfate at this point. It's staying in solution, and it could be so much that it's forming crystals. That's not the white smoke that you're seeing in the K flask. Next up is reaction number 2. That's what I'm going to call this. And in reaction number 2, we're going to take those crystals that you possibly have formed, and we are adding that really concentrated solution of sodium hydroxide. So that NaOH is reacting with the ammonium sulfate, and what we are seeing here is almost like a double replacement that takes place. So the ammonium leaves sulfate and sodium takes its place. So 2 couples go into the bar. Couple number 1, ammonium sulfate. Couple number 2, sodium hydroxide. They are madly in love with each other as of right now, but then they go into the bar and they see each other, and those couples go, hubba, hubba, ooh, I like you, wow. And then that sodium and ammonia decide to switch. So sodium goes in for the kill, and sodium says, get out of here, ammonia. I'm prettier, I make more money, I'm younger, and I'm a better partner because look at me, who doesn't love me? And sulfate says, wow, I thought you would never show up. Kick that other one out of here. I'm tired of him anyway. So what we have is a Na2SO4 that gets formed, and that Na2SO4 is sodium sulfate, but we don't really care about that because that has nothing to do with the Kjeldahl measurement. We don't care about sodium sulfate. We're caring about the ammonia, the nitrogen piece. So where's it coming from? Next up, part of this reaction is that poor little ammonium. Oh, ammonium is so single. And ammonium's like, I don't know what to do with myself. I just got kicked out of a relationship, OH. So would you come by and would you let me know if it's okay if we want to hook up and be partners? And then that hydroxide says, oh yeah, that's perfectly fine. I'm by myself too. So the sodium left me and it went to your partner. So I'm single and you're single. Why don't we kind of make this work? So what happens is that the NH4, so NH4 and the OH come together and they go, ha ha, yay, woohoo, yeah, we're good. So NH4OH is actually formed quickly, but it doesn't stay that way. And then what happens is that we have a breakdown. And that breakdown's like, hey, yeah, this was fine, but, this was just like a rebound, and I'm out of relationship, and now I'm over it, and you were okay, you were there, so I took it out all on you, but at the same time, this is just not going to work long-term, ammonium, so I hate it for you, but we're splitting ways. And then ammonium goes back, and it goes, I don't know what to do, and it breaks down, right? Ammonia has like a mental breakdown, and what it generates is NH3 instead of NH4. So one of the hydrogens breaks off in its breakdown, and that H and that OH is like a match made in heaven, and look at what that makes. It makes water. So this is how the breakdown of the ammonium crystal happens. That ammonium sulfate breaks down, makes some products. Now you know what those products are. And those products, one of which is NH3 ammonia gas. That ammonia gas is going to get released, and that ammonia gas now immediately goes up into your condenser and down into your receiving flask. And that is why we say very often this is a key step, because as soon as you add the ammonium hydroxide, it is over. You're in it to win it. It is all, at this point, on you. You cannot turn back. You cannot stop. This is what you're going to have to go all the way to the end for. Reaction number 3 is the capture of the ammonia. So what's happening here is that in that receiving flask, you will have an acid, and that acid actually looks like this. I know that looks weird, but this is a form of boric acid. And I know it doesn't look like an H is by itself, and I know that it looks like OH is there together and it looks like a base, but it's not. So this is a acid. Boric acid is what that compound is representing. That boric acid is going to be mixed in with some water because it's diluted. There's other stuff that's there. And that is going to react with the ammonia that's coming over from your sample. And the boric acid and the ammonia will react together, and it will generate ammonium again. So it's like, okay, you had your mental breakdown, you went to the doctor, and we fixed it. So you can go back and you can be ammonium again, just like you were when you were single before you met that person that you were in a relationship with. It is perfectly okay to be who you are, and don't let that person get to you. Don't let that person drag you down. Don't let that person destroy your life. And there is more to you than that other person that you were in a relationship with. And be that person, ammonium. And ammonium says, you know, I feel really good. Thank you for the pep talk, doc. Now, here is my $1,000 medical bill, and ammonium, you need to pay that before the end of the month or we'll take you to court. So ammonium's like, okay, I'll get it together, I'll fix myself, and ammonium is perfectly okay back in that solution. But at the same time, what we're seeing here is this BOH4 now that carries a negative charge. You know, something had to happen. Something had to go on with this boric acid in order for ammonium to go from NH3 to NH4. So water had to do something. This boric acid had to do something. So we start to see a change in the receiving flask at this moment. Now, one version of Kjeldahl, and this is probably not going to be the version that you are going to use, but one version of this is this BOH3 that is left over, right? That is the boric acid, and the water that is left over can be titrated. And this is where our back titration comes in. Now, in this case, they're using sodium carbonate, but really that's a base, and any base will work, and any base kind of generates the same type of reaction. It is an acid neutralizing reaction. That's all that's going on here. So a base is a base. Who cares what it is? And I don't really care what it is, but we are measuring the amount of acid that is left over. And in this example, sodium carbonate is used, but it could also be sodium hydroxide. It could also be potassium hydroxide. It could also be any base that will neutralize an acid. Who cares? I don't care what it is. It's something. So go for it, right? It doesn't matter. That's the beauty of it. So an acid and a base reaction begins to take place, also known as a neutralization reaction. And what happens is that we are destroying the remaining acid that is left over. So once we get to the drip, 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 drip of the titration, at some point in time, a color change will take place. And that color change is a time to stop. And that color change is letting you know no more acid is left over. It is now actually all used up. And this is where you stop. And this is what you do calculation-wise with the number of milliliters that it took in order for you to get to that point. Now, phenolphthalein is not used for these reactions most of the time. What is used is something like methyl orange, right? That is one option of many, but I do not think that we even use methyl orange in the reaction scenario that we give you based on what we choose as a base. There's other options that are out there, again, modifications, and if it's not methyl orange, it will be another indicator or a mixture of two indicators. That's normal too. A mixture of two indicators that could take place in that reaction to give you the color change of where this should take place. Finally, Kjeldahl, keep in mind, process is long, concentrated bases, very concentrated acids, very high heat, and bumping can be a problem. What bumping is that in the heat period, as you begin to put flame onto the bottom of this flask, you got liquid solution in here. Depending on what reagents you have used, it can bump. And it literally will bump. It will generate so much heat, it will boop, 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 boop. I mean, that's what it does. It will actually sound that way sometimes too. It's not just made up. And it could be so violent that your flask can actually move on the ring or in the clamp. I mean, that's how hard this thing can bump if you're not careful. So that is another reason that different options are out there. Depending on the samples that you're using, we want to minimize that when we can. So once more, those reagents can change a little bit over a course of time with us as we give them to you year after year. Multiple samples, are also a thing. Oh my God. Could you imagine doing this with 20 samples at one time? Who's got the time for all of this? So we need something a little more organized. We need something a little bit better. And that's going to be a drawback unless we have instrumentation or some type of setup like you're seeing this woman use here in the processing or in the testing of it. So automation is great whenever we can do it. So overall, I think that you get kind of the drift of Kjeldahl. At least I hope you do. We're going to take our fertilizer, add sulfuric acid that's generating ammonium sulfate crystal. Those crystals are then going to be broken down by a base, and that's going to generate our ammonia gas. That ammonia gas is going to get driven off and captured in a acidic solution, and we're going to have leftover acid. And then we're going to take that leftover acid and we are going to react with it through a titration. We're going to titrate it with a base most of the time using an indicator that's not phenolphthalein, but using an indicator in order to figure out where our color change is at. And that is the equivalence point, and that is where we stop. And we write down the milliliters of titrant that it took, and then we plug that milliliter of titrant into an equation that allows us to calculate the amount of nitrogen in the sample, right? The other thing that I want to say is that this is the amount of nitrogen in the sample. Most of the time in these equations, it will be the percent of nitrogen in the sample. So once we use that equation and once we solve for a value, that value is the percent of nitrogen coming from the sample itself. And that percent of nitrogen hopefully should somewhat match the label that is on the fertilizer. So if our fertilizer sample is 10%, we hope that this value is really close to 10%, no matter what my sample size is. I mean, it could be 1 gram, it could be 2 grams, whatever the case is, it doesn't matter. But once I plug the right values into that equation is giving me straight up percent nitrogen. So as you can imagine, the equation that is used in the Kjeldahl method will actually use the sample amount because that is an important number, of course. And that's going to be in terms of gram most of the time, but that's going to calculate automatically, in a way, a percent value for you. So that percent value that you're getting from that equation hopefully should be really close to the percent value that is inside of the fertilizer or on the bag of the fertilizer that we are providing to you in the laboratory. Other than, this one calculation, there's really nothing else that you need to do. There's no spreadsheet work. You'll just fill out the data sheets. You'll just do the calculation by hand. You'll turn it in and call it a day. But it is a lengthy process in order to get to that titration amount. So just be ready, just be prepared for that. I know that you are probably not prepared for a 4th video in TKN that ran 45 minutes, but guess what? You got it, and you did it, and you survived, and you made it through it. And I know that you'll make through TKN as well. All right, so that's the story with total Kjeldahl nitrogen. Keep in mind, it does not measure all nitrogen, just Kjeldahlic forms of nitrogen, and that includes all of our straight up ammonia, NH3, and that also includes our organic forms of nitrogen that will eventually get released as well. But it does not include any nitrates or any nitrites. Those normally stay behind. They do not react the same way. They do not generate ammonia. They do not release. They do not get captured. They do not get titrated. We can modify Kjeldahl, or we can do another type of method in order to measure those if that's what we want. But very often when we do TKN, the word says what we're measuring. Total Kjeldahl nitrogen. And someone with knowledge knows automatically, oh, well, that does not include nitrates and that does not include nitrites. So, in other words, if our fertilizer was made up of some type of nitrogen-containing compound that was NO3 or NO2 based and nothing more, then those would not get measured. It's nitrogen, it's there, but it would not get measured. But ammonium nitrate would partially get measured because the ammonium piece is getting transferred over to ammonia, and that is getting measured. But these nitrates and nitrites are left behind unless we modify and do fancy things. And that's not really what we're going to be doing. So I'm telling you this because I want you to know that the number that you get from this procedure might not exactly match the bag. And if it does not exactly match the bag, then there is a chance that they heavy-handed nitrates and nitrites inside of that fertilizer, and they have claimed that that is your nitrogen content, when in fact it might not be. And your lab methods are not picking up on that. So if there is not an exact match, don't worry. I'm not taking off for percent error. I'm not taking off for percent yield. I'm looking for the process, the technique, and the advanced lab method, because that's the title of the class. All right, so I'll be ready for you when you want to do the Kjeldahl. Good luck. Make sure you get up nice and early in the morning and come in and see me, and I'll be here ready when you want to do it. I normally don't have these set up more than one or two of them at a time because they are elaborate and they take up a lot of glassware. So people can bottleneck if they wait till the last minute, and I'll try to do it at once. So don't be that person. Come in on random day and be like, I'm here to do Kjeldahl, yay! And I'll be like, yay! We get it done and we get it over and you don't have to worry about it later.